Two loudspeakers situated at A and B are separated by a horizontal distance of 6 meters. O is the midpoint of AB. Here is O. A detector of sound moving parallel to AB at a perpendicular distance of 8 meters. So it is moving parallel to this AB at a distance of 8 meters, like this, along PQ. The sound detector records a maximum sound at P. So here the first maximum sound is recorded, and another maximum sound at Q, which is vertically opposite to B. So vertically opposite to B, there is another maximum sound recorded. Second maximum is heard here. Now the question is, what is the wavelength of light? Now first maximum sound is recorded at P. It is obvious because the sound traveling from A, which is traveling towards P, and the sound starting from B, which is traveling towards P, they are traveling equal distances. So they don't have any path difference. So they shouldn't have any phase difference by the time they meet at P. So when these two waves, A and B sound waves, by the time they reach at P, the crest should fall on crest and trough should fall on trough, so that it results in constructive interference and producing a maximum sound at P. Now, what happens by the time they meet at Q? And they say that there is a second maximum sound, and this is possible when the sound traveling from A by the time it reaches Q, and the sound traveling from B by the time it reaches Q, again the crest should fall on the crest. And that is possible when the path difference between these two waves should be 1 lambda. And so the distance AQ and the distance BQ, that difference should be 1 lambda. Then only it is possible to have maximum interference pattern here. So AQ minus BQ must be equal to lambda, 1 lambda. But you can find out AQ using Pythagoras theorem. AQ is equal to square root of this 6 square plus 8 square. That is that comes to square root of 100. That is equal to 10 meters. And so that implies lambda is equal to AQ is 10 and BQ is 8. So that is equal to 2 meter. So that is the wavelength, and the answer is 2. A sound wave of wavelength 32 centimeter enters the tube at P as shown in the figure. So here it enters, and the minimum value of the radius for which the sound at Q is maximum. Now the problem is like this actually. When the sound enters here, it finds two paths here. So it splits into two parts. So one part moves straight like this, and another part of the wave moves through the circular, semicircular path and meets the other one here. Now, when it meets the other one here, we don't know whether it will meet with the crest on crest or trough on trough, whether it is constructive interference or destructive interference. So their condition is you have to hear the maximum sound at Q. If maximum sound is to be heard at Q, the crest should fall on crest. That means the condition for bright fringe or maximum intensity is to be applied. The condition for maximum intensity is path reference delta x must be equal to n lambda, and they are asking you the minimum value of r. So minimum value of the radius, the extra distance traveled by this one should be n lambda. Now for minimum condition, we will put n equal to 1. So let us assume that this wave which has moved in the semicircular path, which has traveled more, and that extra distance is 1 lambda. So path difference delta x should be equal to 1 lambda, and path difference can be written as this path length minus this path length, and that can be calculated as this path length is the whole circumference by 2. So 2 pi r by 2, that is pi r minus this one. This is the diameter 2r, twice the radius. That must be equal to 1 lambda. Now pi is, so I will take r outside the bracket. They are asking you what is the value of r. 3.14 minus 2 is equal to, lambda is 32 centimeter. It is a sound wave. So r is 32 centimeter divided by, this is 1.14. So if 32 is divided by 1, then the answer would have been 32, but it is slightly greater than 1, so it should be less than 32, just less than 32. So it is 28 answer. two sources are placed on x-axis at a separation of d equal to 3 lambda. So this is given to be 3 lambda. S1 and S2 are placed at a distance of 3 lambda. Let me write it here. An observer starts moving from A on a circular track of radius r. So an observer starts from A, moves to B, then back to A in the circular track. How many bright points and dark points will he observe? When the observer moves from A to A, how many dark and bright points will he observe? Now we will analyze it like this. Let us imagine that a number of screens are placed on the circumference of this circle. Light starting from S1 and S2, when they fall on different screens like this, what type of fringes they will form? That will give you the answer for their question. Now we know that for the formation of bright fringe, the path difference needed is n lambda, where n corresponds to 0 means there is no path difference, n is equal to 1 means a path difference of 1 lambda, so on. Now let us imagine a screen placed here. If a small screen is placed here, light coming from S1 should travel like this and it should meet the screen here. Light traveling from S2 should travel like this and it should meet the other wave here. They don't have any path reference. S1 and S2 are symmetrically placed about the center of the circle. So the path traveled by S1 while reaching B and path traveled by S2 while reaching B are same. So they don't have path reference. Path reference is 0. That corresponds to the first maxima. And now this corresponds to n equal to 0 then. This is the first maximum produced. That is, now let us consider a screen placed here at the circumference at A. The wave which is traveling from S2 here has to travel a lesser distance because this point is very close to S2. Whereas the wave starting from S1 has to travel a longer distance by the time it reaches A. How much longer? That is this one. This is the extra distance that S1 has to travel so as to reach A than S2. So the path difference between the waves starting from S2 reaching A and S1 reaching A is equal to 3 lambda. So here the path difference is 3 lambda. If the path difference is 3 lambda, that should correspond to the third maximum, n equal to 3. That means if you place different screens at different points of the circumference of the circle, there should be a screen here, a point here, at which the wave traveling from S1 reaching at this point and the wave traveling from S2 reaching at this point, they should have the path difference of 1 lambda. N should correspond to 1. And again, there should be another point here at which the wave started traveling from here to here and here to here should have a path difference of 2 lambda. And n equal to 3 corresponds to the point here. So n equal to 1 and n equal to 2 should be coming in between. That means when you move one quadrant of the circle from A to B, you should get a maximum, and maximum. You should get 3 maximas in between. And between 2 maximums, there should be a minima. That means there should be a dark fringe here, here, and here. And therefore, in a one quadrant, you get 3 maximas and 3 minimas. And totally, you should get 12 maximas and 12 minimas. Suppose you start counting from here, 1, 2, 3, and 4, 5, 6th maxima, 7, 8, 9, 10, 11, 12. So 12 maximas and 12 minimas. So one answer is correct. Now, how can, and there is no other 12 here. So how it should be pi by 6. Now you should get one maxima here, another maxima here. Then 2 maximas here, 2 maximas here. So it totally 90 degree has to be divided for 3 maximas. So angular positions of maximas and minimas. Angular positions if you want, then the pi by 2 angle must be divided for 3 maximas. One maxima here like this, another maxima here, and another maxima here. So it is totally pi by 6, that is 30 degrees. So answer should be third one. Intensity ratio of two coherent sources is 81:1. The ratio of maximum to the minimum intensity in the interference pattern is 81:1 is the intensity ratio of the two individual sources. We know that intensity is equal to 2 pi square f square a square rho v. So for a wave, f is the frequency, a is the amplitude of the wave, rho is the density of the medium where it travels, and v is the speed. And it is directly proportional to amplitude. So if you just take this relation, then intensity ratio is given. We can find out what is the amplitude ratio. So I1 by I2 for the two sources is equal to A1 square by A2 square, that is equal to 81 by 1, because intensity is directly proportional to square of the amplitude. So that implies A1 by A2 must be equal to 9:1. Now their question is, what is the intensity ratio in the interference pattern? You know that in the interference pattern, maximum intensity is the position where amplitudes add up, and minimum intensities are the positions where amplitudes, they get reduced, they get subtracted. So the maximum intensity to the minimum intensity ratio must be equal to A1 plus A2 whole square divided by A1 minus A2 whole square, because at the maximum intensity position amplitude should add up, but intensity is directly proportional to square of the amplitude. So this is equal to 9 plus 1 whole square divided by 9 minus 1 whole square, and this corresponds to 10 square, that is equal to 100, and this corresponds to 8 square, that is equal to 64, and this comes to 4 25s are and 4 16s are, and option is 3. The intensity at the maximum in a Young's double slit experiment is I naught. Distance between the two slits is d is equal to 5 lambda, where lambda is the wavelength of light. What will be the intensity in front of one of the slits on the screen placed at a distance of capital D is equal to 10 into small d. Now let us visualize this diagram. If you have two sources of light, S1 and S2, separated by a distance d, and it is given d as 5 lambda, so that is 5 lambda. And if you place a screen here, which is at a distance of capital D, it is also given 10D, and small d is 5 lambda. So you can write this as totally 5 lambda into 10, 50 lambda. Now let us select a point which is at the center of the line joining the two sources. Now the vertically opposite point is here. Definitely this will be a bright fringe, because the wave starting from S1 and reaching here, S2 reaching here, they will not have any path difference. So they meet constructively to produce bright fringe. Now their question is, and here intensity should be I naught, maximum intensity. Their question is to find out what is the intensity at a point which is directly opposite to one of the slits. Now you select this point, which is directly opposite to one of the slits. Its distance from here, if I take it as x, then that x is nothing but d by 2. Now if you have such a point, and if you know the distance from the central bright fringe to that point, you can find out what is the path difference between the waves meeting here. The wave 1 which is starting from here and reaching here, and the second wave which is starting from reaching from S1 and reaching here, they will have a path difference, and they will also have a phase difference. That's why they produce different intensity here. So what is the path difference between the two waves starting from S1 and S2 reaching a point, that point which is lying at a distance of x from the central plane? That is given by path difference delta x is equal to x d by d. This is the formula. And if you want to calculate what is the path difference between these 2 points, delta x is equal to x, and the small d is 5 lambda by capital D. Capital D is this 10D, and this is equal to 50 lambda. That is equal to, and x is d by 2. So x is d by 2, and again, okay, I will substitute d by 2, and this is lambda will get cancelled. Then it is 1 by 10. That is equal to, and d is equal to 5 lambda divided by 20. So this is lambda by 4. Now you have got the path difference. So what is the phase difference between these two waves reaching here? Phase difference is equal to 2 pi by lambda into path difference. That is equal to 2 pi by lambda into path difference is lambda by 4. So that comes to lambda gets cancelled, pi by 2. Now once you know what is the phase difference between the two waves and producing some intensity at a point on the screen, you can find out what is the intensity with respect to the maximum intensity of the central fringe. So that intensity of any two waves reaching a point on the screen is equal to I naught cos squared pi by 2. Or phi is the phase difference. That is equal to I naught is I naught itself here, cos square pi by 2. So this gives the answer is equal to, cos squared phi by 2. So cos squared pi by 2 by 2. So that gives answer I is equal to I naught cos square pi by 4, because it is 5 by 2. So pi by 4. Cos pi by 4 is 1 by root 2. When you square it, you get half. So this is I naught by 2. So this is the intensity here at a distance d by 2 from the central fringe. So answer option is fourth one, I naught by 2. In Young's double slit experiment, two coherent sources are 0.9 millimeter apart. If the second dark fringe is at a distance of 1 millimeter from the central fringe on a screen at 100 centimeter away, the wavelength of light used is. Now, suppose you draw the double slit experiment setup, it will be like this. And here are the two sources of light, S1 and S2. And here is the screen. And this is the vertically opposite point where we get the central bright fringe. And we will get the next bright fringe here and the next bright fringe here like this. And all the bright fringes are situated at a distances of some betas. For example, this is 1 beta, this is 2 beta. So this corresponds to the 0th fringe, and this corresponds to the first bright fringe, and this is the second one, this is the third one. So first bright fringe is at a distance of 1 beta, second bright fringe is at a distance of 2 beta, third one is at 3 beta. So if you are asked to find out what is the distance of any bright fringe, then it is n beta. N corresponds to 1, 2, 3, etc. First bright fringe, put n equal to 1. Second bright fringe, put n equal to 2. Now, if you go on counting where are the dark fringes, suppose I mark the dark fringes in a red color like this. This is the first dark fringe, and this is the second one, and this is the third one, and like so on. Now, the first dark fringe, there is no central dark fringe. The first dark fringe itself is situated at a distance of half beta. So, the second dark fringe is at a distance of 1.5 beta, 1 plus half. So second dark fringe is at a distance of 1.5 beta. What about the third dark fringe? 1 beta, 2 beta, and 2.5 beta. So if you go for the third dark fringe, it will be at 2.5 beta. So in the same way, suppose you want to know what is the distance of second dark fringe, it is 1.5 beta. So distance is given. If the second dark fringe is at a distance of 1 millimeter, so 1 millimeter should be is equal to 1.5 beta, because it is the second dark fringe which is situated at a distance of 1.5 beta. So if it is 1.5 beta, then I can write it as 1 millimeter, 1 into 10 to the power minus 3 is equal to 1.5 lambda d by d. That is the formula for fringe width beta. 10 to the power minus 3 is equal to 1.5 into, now the lambda has to be found out, and the d is 100 centimeters, that is 1 meter, and small d, the distance between the two sources, 0.9 millimeter, 0.9 into 10 to the power minus 3. So that implies lambda is equal to 0.9 into 10 to the power minus 6, minus 3 divided by 1.5. And this is 6 times usually. And you see the options here, 400, 450, 500, and 600. 9 by 1.5 is always, it is 6 times. So whether it is 60 or 600 or 6,000, never mind. This is the only answer that we have, 600 nanometer. Two parallel slits separated by a distance of 0.3 millimeter and illuminated by monochromatic light give an interference pattern on a screen 1.5 meter away from the slits. If the fourth bright fringe is at a distance of 1 centimeter from the central maximum, then the wavelength of light used is. So all the bright fringes from the central maximum are equally spaced at equal betas. Beta is the fringe width. So fourth bright fringe will be at a distance of 4 beta. So it is given that 4 beta is equal to, so fourth bright fringe is at a distance of 1 centimeter, 1 into 10 to the power minus 2. So 4 into lambda d by d is equal to 10 to the power minus 2. 4 into lambda, wavelength of light used, that is the question to be answered now, into d, the distance of the screen from the slits is 1.5 meter. The distance between the slits is 0.3 millimeter. 0.3 into 10 to the power minus 3 is equal to 10 to the power minus 2. So lambda corresponds to 0.3 into, this is 10 to the power minus 5 divided by, this is 6. And the answer should be like this. Here you have different options here: 1,000, 750, 250, 500. So just play with the numbers. 3 by 6 is a half. Half corresponds to 5. So it should be this answer, 500 nanometer. In a Young's double slit experiment, slits are separated by 2 millimeter and the screen is placed at a distance of 1.2 meter from the slits. Light consisting of two wavelengths, 6,500 angstrom and 5,200 angstrom, are used to obtain interference fringes. Then the separation between the fourth bright fringes of two different patterns produced by the two wavelengths is. Now you have to find out where is the fourth bright fringe of 6,500 angstrom and where is the fourth bright fringe of 5,200 angstrom. What is the separation between them? So for that we will take the central fringe as the reference. Find out the distance of the fourth bright fringe of this one from the central fringe. Similarly, find out the distance of the fourth bright fringe from the central fringe for this wavelength. Take the difference. That will give you the answer. For example, in the screen, and if this is the central bright fringe, and if this is the first bright fringe, fourth bright fringe of the first wavelength, and if this is the fourth bright fringe of the second wavelength, find out this distance. It is 4 beta for this wavelength, and find out 4 beta for this wavelength. Take the difference. That will give you the answer. Now 4 beta for the first wavelength, that is 6,500 angstrom. I can do it like this. So 4 beta, that is the distance of the fourth bright fringe from the central fringe. 4 beta is equal to lambda 4 into lambda d by d. That is equal to 4 into lambda. Lambda is 6,500 angstroms. D, capital D is here it is 1.2 meter divided by small d. Small d is 2 millimeter. Now this will be is equal to 4 into 6,500. This I will divide 0.6. 4 into 6,500 is 0, 0, 20 and 26 into 0.6 into 10 to the power minus 7, because this 10 to the minus 3 will go up and it will be plus 3. Now multiply 0.6 to this 26000. Now I will donate 1 0 to this one so that this becomes 6. So 6 into 2,600, that comes to 6 0. So this 0, and 6 are 36, and 6 2s are 15. 12 plus 3 15. So into 10 to the power minus 7. That corresponds to, and you see all the answers are in millimeter. So I will take minus 4 from here. 1, 2, 3, 4. 1.56 millimeter. This is 1/4 bright fringe due to one pattern. Now let us find out the fourth bright fringe due to another pattern. That is due to 5,200 angstrom. For that one, 4 beta is equal to, directly I will substitute 4 into 5,200 angstroms minus 10 into, and d by d remain the same, 1.2 divided by d is 2 into 10 to the power minus 3. Again this 2 will be 0.6 times, that is equal to, now 4 beta, 4 into 5,200, 0, 0, 8 and 20 into 0.6 into 10 to the power minus 7. Again minus 3 goes up and it becomes plus 3 and minus 10, 10 to the power minus 7. Now multiply this 2080, 10 donate it here, it becomes 6. 2080 into 6, that comes to 6, 0, 8, 4, and 12 into 10 to the power minus 7. So that corresponds to 1.248 millimeter. So fourth bright fringe of this wavelength is at 1.56 millimeter, and the fourth bright fringe of 5200 angstrom is at this distance. So what is the distance between them? So get the difference between them. 1.56 millimeter minus 1.248 millimeter. So that corresponds to 2, and this will be 5 minus 4, 1, and this 0.312 millimeter, option 1. Two coherent point sources S1 and S2 are separated by a small distance d as shown in the diagram. The fringes obtained on the screen will be whether they are concentric circles, points, straight lines, or something else like semicircles. Now, the S1 and S2 are in the same straight line in front of the screen. Now, suppose the wave starting from S2 reaches the screen somewhere here, and the wave starting from S1 reaches the screen here, and they will have a path difference. And the same, and say this path difference produces a bright fringe here. The same condition will be obtained here also, here and here. And if you imagine this screen to be a two-dimensional plane like this, then you can guess the same type of path difference and same type of intensity will be formed on a circular pattern like this. And similarly, you can guess, suppose the waves starting from here and here meet here, again they meet here and produce another bright fringe, and such type of patterns will be produced in a circle. So if the sources are in a linear fashion like this, then the fringes are in circular pattern, option 1. In Young's double slit experiment, red and blue lights are used. The wavelengths of red and blue light are 7,800 angstroms and 5,200 angstroms respectively. If the nth red band coincides with the n plus 1th blue band, then the value of n is. Now, usually on the screen, whenever suppose this is the central bright fringe, whenever the fringes are produced, suppose this is the third or fourth, 1, 2, 3, 4, fourth bright fringe of red, then so blue fringes are very close to each other because their wavelength is less, so fringe width is less. So if this is the fourth red fringe, then the blue fringes may be produced very closer like this, like this, like this. So here again a blue fringe is produced at the same place where red fringe is produced. So this is the first blue fringe, second one, third one, fourth one, fifth one. So n is equal to 5 for blue and n is equal to 4 for red. Both are produced at the same place. From the central fringe, if they are separated by, if they are at a distance x is same for both. And usually we write x as n beta, which is equal to n lambda d by d. So this n lambda d by d must be same for both the wavelengths. So we will equate it. Now you write the n lambda d by d for the red wavelength. Nth fringe, its nth fringe is, of course, this n will vary. For one it is 5, another one it is 4. So this is an example, that's all. And here now, nth fringe of red, n into lambda 7,800 angstroms, capital D by small d must be equal to, because this is the position of the nth red band. At the same place, n plus 1th blue band should be produced. That is equal to n plus 1th blue wavelength. Blue wavelength is 5,200 angstroms. And capital D and small d will not vary. It will be same for both the colors because the setup is same. Now, so capital D, small d will get cancelled. Angstroms 10 to the power minus 10 will get cancelled. So n into 7,800 must be equal to n plus 1 into 5,200. Now it's your job to find out n, value of n. So n by n plus 1 must be equal to 5200 by 7800. Two zeros will get cancelled. So this is a 226 239 and if you cross multiply, 39n must be equal to 26n plus 26. Now if you subtract it here, 39 minus 26, this is 13n. So 13n must be equal to 26. That implies n is equal to 2. So third option. When a drop of oil spread on water surface, it displays beautiful colors in daylight because it acts like a thin film. A drop of oil on the surface of water or soap bubble that acts like a thin film. Even the coating given to the lens in a camera, it's so thin that the light undergoes interference as it passes through it. So because of multiple reflections from the two surfaces of the thin transparent coating, or even in the thin transparent that oil layer formed on the surface of water, so these multiple reflected lights interfere and they produce interference pattern, and that will be colored, and the answer is 3. In Young's double slit experiment, the separation between the slits is hard and the distance between the slit and the screen is doubled. The fringe width is, we have the formula for fringe width as beta is equal to lambda d by d, where d is the distance from the sources to the screen and d small d is the distance between the sources. Now here, the separation between the slits is hard. That means this is made half, and the distance between the slit and the screen is doubled. So this is double. So in the new formula for beta, you will have a half here and you will have a 2 here extra. So totally you will have, these 2 will come to the numerator. You will have 4 more. So the new value of fringe width will be 4 times the old fringe width. So answer is quadruple. In Young's double slit experiment with monochromatic light, fringes are obtained on a screen placed at some distance from the slits. Distance is not given. If the screen is moved by 5 centimeters towards the slits, so if the screen is moved by 5 centimeters towards the slits, then the new distance will be 5 centimeter less because screen is moved nearer to the slits. Then the change in the fringe width changes by this much, and if the separation between the slits is 1 millimeter, what is the wavelength of light? So question mark is for wavelength. Separation between the slits is 1 millimeter. Now here, how to take this 3 to 10 to the minus 5? That is a change in the fringe width. Shall we add it to the old fringe width or shall we subtract it from the old fringe width? In order to analyze this, the formula for fringe width is beta is equal to lambda d by d. Now here, if the screen is moved by 5 centimeter towards the slits, that means this capital D is made less by 5 centimeters. So the new value of D will be D minus 5. So when D decreases, automatically beta decreases. So the new value of beta should be 3 into 10 to the power minus 5 meters less. So we will write 2 equations for this. The first beta is equal to lambda d by d as it is. So this is equation 1. The new value of beta, that is beta minus 3 into 10 to the power minus 5, because fringe width will be changing by this much. So they haven't given whether it is decreasing or increasing. We have come to the conclusion that it is decreasing because of the reason that the screen is moved towards the slits. That means capital D is decreased. So beta should decrease. That is equal to the same wavelength lambda is used, and capital D is the new value is D minus the old one 5 centimeter divided by that small d is not at all changed. So this is equation 2. We will subtract the two equations now. Because if you divide it, lambda will be lost, and lambda itself is a thing which has to be calculated. So we will subtract the two equations here. Left hand side, beta minus beta, and this becomes minus of minus plus. So 3 into 10 to the power minus 5 is equal to. So here lambda by d is a constant. So you can take it outside before subtracting. Lambda by d into this one d minus this d plus 5 into 10 to the power minus 2. Hope you can follow this. Lambda by d is a constant. So take it outside. This d minus, or we will write it, d minus this d plus 5 into 10 to the power minus 2. So the answer will be going like this. So 3 into 10 to the power minus 5 is equal to lambda divided by, and this d is given 1 millimeter, so I can substitute it 1 millimeter. This d minus d has been cancelled, and 5 into 10 to the minus 2 will remain here. 5 into 10 to the minus 2. And you see the answers, different numbers, 3000 angstroms, 4500, 5000 and 6000. So just play with the numbers, it is enough. Because all are angstroms, that's very much sure. This 5, when it comes to the denominator here, 3 by 5 you will get. 3 by 5 is 0.6, so it should be 6,000 angstroms. When one of the slits of Young's double slit experiment is covered with a transparent sheet of thickness 4.8 millimeter, the central fringe shifts to a position originally occupied by 30th bright fringe. What should be the thickness of the sheet if the central fringe has to shift to the position occupied by 20th bright fringe? Now, when one of the beams of the double slit experiment are disturbed by placing a glass slab or some other medium, then one of the beams have to travel through an extra medium, so their path reference will be lost. Of course, the fringe width doesn't change. All the fringes will get shifted to a position. Originally occupied positions of the fringes will not be found later after introducing that transparent medium to one of the beams. The whole pattern will get shifted. Beta remains the same. Now, shift in the fringe or fringes when a thin film of thickness T is introduced in one of the path of one of the beams is x is equal to beta by lambda into mu minus 1 into T, where T is the thickness of the transparent medium which is disturbing one of the beams, mu is its refractive index, beta is the fringe width which doesn't change even after introducing the transparent medium, and lambda is the wavelength of light. Now, if you go on writing the values for the two cases given here, first of all, they are introducing a medium of thickness 4.8 millimeter. That makes the central fringe to shift to 30th bright fringe position. That means this x can be written as 30 beta, because the central fringe goes to the position of 30th bright fringe. 30 beta is equal to beta by lambda into mu minus 1 into thickness is 4.8 millimeter. So I will take it as equation 1. Now, what should be the thickness of the sheet if the central fringe has to shift to the position occupied by 20th bright fringe? In the original fringe pattern, if the 20th fringe is at a certain distance, after introducing the medium, the central fringe should go to that position of the 20th bright fringe. So if it has to be like this, then the new equation can be written as, if it has to be 20 beta, if x has to be 20 beta, beta by lambda, the same type of medium, but thickness is different, T. What is this? This is the question mark. And if you divide this easily, then here you will get 30 by 20. Beta will get cancelled. Beta by lambda gets cancelled. Mu minus 1 gets cancelled. 4.8 millimeter divided by thickness. So finally, thickness is, that implies T is equal to 4.8 millimeter into 20 divided by 30. Okay, 0 will get cancelled. This is a 1 za, 6 za. So this will be, thickness will be 3.2 millimeter. Answer is option 2. With monochromatic light, the fringe width obtained in a Young's double slit experiment is 1.33 millimeter. The whole setup is immersed in water of refractive index 1.33, fringe width is. So when the whole setup is immersed in water, we'll have the formula for beta is equal to lambda d by d. The distance between the screen and the source will not change. Distance between the slits will not change because it doesn't depend on the medium. And the wavelength of light changes. Whenever a light travels into a medium from air to medium, say, then its new wavelength lambda dash is equal to lambda by mu. So the new fringe width beta dash is equal to beta original one by mu. That's all. So beta, the original fringe width is 1.33 millimeter divided by mu. Mu is the medium in which it is immersed is 1.33. So that comes to 1 millimeter, option 2. Corpuscular theory was able to explain the phenomena of. Now, corpuscular theory was able to explain the reflection and refraction, but it fails to explain simultaneous reflection and refraction. That's all. So you can select this option, both 1 and 2. It was able to explain these two. The phenomena which proved that light is transverse in nature is, the answer is polarization, because only those waves which are transverse in nature can be polarized. So if at all a wave shows polarization property, then it should be a transverse wave. Light shows polarization. That's why light is a transverse wave. Yeah, sound waves cannot be polarized. So sound wave is not a transverse wave, it's longitudinal. So the property which proves that light is transverse in nature is polarization. This question is asking you the angle between the electric field, magnetic field, and the direction of propagation of the wave. Obviously, it is 90 degrees. The concept of quantum nature of light has emerged as an attempt to explain. Actually, Max Planck proposed quantum theory just to explain black body radiation. Later on, it was used by Albert Einstein for explaining photoelectric effect also. But initially, it was proposed to explain black body radiation. So option 1. Electromagnetic waves are generated and detected for the first time by, actually, James Clerk Maxwell. He proposed the theory of electromagnetic waves. He didn't prove it practically. Practically, it was demonstrated and proved by Henry Church. So proof goes to Hertz and proposed by Maxwell. In an electron microscope, if the accelerating voltage is increased from 20 kilovolt to 80 kilovolt, the resolving power of the microscope will become. Now, resolving power of a microscope is always inversely proportional to the wavelength. That is one of the method followed in increasing the resolving power. Decrease the wavelength and increase the resolving power. That's why we have arrived at electron microscopes. Because electron microscopes use the principle of wave nature of matter. A moving particle exhibits wave nature, and the wavelength associated with any moving particle is lambda is equal to Planck's constant divided by square root of 2mqv. I have used, actually lambda is equal to h by momentum. I have expanded momentum in this term because I am interested in accelerating charged particle. So if a charged particle of mass m and charge q is accelerated through a potential difference v, this is the de Broglie wavelength. Now, we have to get the relation between increased potential and the resolving power. So here is the connection. De Broglie wavelength is inversely proportional to square root of accelerating potential. So lambda is inversely proportional to square root of accelerating potential, and resolving power is inversely proportional to wavelength. Now here, if you note it, the accelerating voltage is made 4 times the initial value. When the accelerating voltage is made 4 times, lambda becomes half of the previous value, because when you substitute V as 4V, 4 times the original value, you will get an half extra in this formula. So lambda dash becomes half of the original value. When the lambda gets halved, resolving power should get doubled. So this should be the answer. So de Broglie wavelength is inversely proportional to square root of potential, but potential is made 4 times now. So the new case will have 4 times more potential, which will give you half of the de Broglie wavelength as earlier. And when the de Broglie wavelength is made half, 2 comes to the numerator, resolving power gets doubled. Option D. Two telescopes have objectives of diameters 0.1 meter and 0.15 meter respectively. The ratio of their resolving powers for a light of wavelength 5800 angstroms. Wavelength is a constant, so only the varying factor is diameter of the objectives. Resolving power of a telescope is directly proportional to the diameter, d by 1.22 lambda. So sorry, is equal to. So resolving power is directly proportional to the diameter. So resolving power of the telescope RP1 by RP2 is equal to D1 by D2. That is equal to diameter is 0.1 and 0.15, and that becomes 10 by 15 if I multiply and divide by 100. So that is equal to 2 za 3 za. 2:3. Option B. Light of wavelength 550 nanometer is incident normally on a slit of width 0.2 millimeter. The angular position of the first minimum on one side in radians is. Now, if you visualize the single slit diffraction, if this is the screen, at vertically opposite point, you will get the brightest region, and the brightness goes on decreasing as you move away from the vertically opposite point to the slit. If the brightness decreases, we get a minimum and maximum like this. So these are all secondary maximas, and this is the central maximum. And at the center of the central maximum, brightness will be highest. And here we will have minima, that is the dark fringe. Now, if the waves which are diffracted at an angle theta, and they will interfere and produce a minimum here. So let this be the angle of diffraction, theta. Then we know the condition. If A is the width of the slit and if D is the distance between the slit and the screen, the condition for diffraction is A sine theta is equal to n lambda. And this is the condition for dark fringe. And we are going to the first dark fringe. That means it is the half of the width of the central maxima. And I'll call this as X. This is the half width of central maxima. And this is the angular width of the central maxima. Now, when theta is very small, sine theta can be taken as almost equal to theta. And since n is equal to 1, since it is the first minima that you are finding, because the angular position of the first minimum, so substitute n equal to 1, and theta is very small, A theta is equal to 1 lambda, and you can write theta is equal to lambda by A, that is equal to, lambda is 550 nanometer, and A, width of the slit is 0.2 millimeter into 10 to the power minus 3, and if you, sorry, 0.22 millimeter, and if you divide this by 11, 5 times 11.01 times. So if you calculate theta, angular width, theta is equal to 0.02 times, sorry, 0.02. Then, so this is 50 into, I will take this as 2 So here is a 10 to the power minus 2, 10 to the power minus 5, and totally 10 to the power plus 5, plus 5 minus 9, 10 to the power minus 4 by 2. So 2, there is a 10 to the power minus 2 here, minus 5, plus 5, and minus 4. So that is equal to 25 into 10 to the power minus 4 radians, and theta is equal to 25 into 10 to the power minus 4 means 0.0025. So option is 1, first option. Light incident at the polarizing angle suffers a deviation of 30 degrees. The refractive index of the medium is. Now, when a ray of light is incident at the polarizing angle, we know that the reflected light is completely polarized and refracted light is partially polarized, and at the polarizing angle this is completely polarized, so I will call this as IB, and this angle of reflection is also IB. These two will be at 90 degrees, and we know the Brewster's law. And at this condition, and if this is the angle of refraction, then we have angle of deviation, that is the angle between the original direction and the final direction. This one, angle of deviation, is equal to this total. This is a straight line and this is a straight line. This total angle will be I. It is a vertically opposite angle to IB. Okay. D is equal to IB minus R if you want to have this angle of deviation. But according to Brewster's law, this IB plus R must be equal to 90 degrees. 90 is equal to IB plus R. Now, if I substitute the value of angle of deviation given here, this will be 30 degrees equal to IB minus R. So take it as equation 1, take it as equation 2. They're asking you to find out the refractive index. We know the relation between refractive index and the Brewster's angle, tan IB is equal to mu. So if you add these two equations, you will get IB. So 120 is equal to 2 IB. R will get cancelled. IB is equal to 60 degrees. And tan 60 is equal to the refractive index of the medium, which is reflecting and refracting the light. And tan 60 mu is equal to √3. That is equal to 1.732. Option 3. Two Polaroids are set with the transmission planes at 45 degrees. What percentage of light is transmitted? Now, suppose you have an unpolarized light and you have to take it as two Polaroids are kept at 45 degrees. So the incident light is unpolarized. Suppose one Polaroid, first one is like this, and the second one Polaroid is at 45 degrees kept a little away like this. Then when light is incident on the first Polaroid, that is unpolarized, so like this, and then it gets polarized and its axis of vibration will be in some plane, and it will be incident on the second Polaroid, and then finally it comes out. So what is its intensity here compared to the original intensity I naught? Usually when a unpolarized light, this is unpolarized light and this contains vibrations in all directions. Suppose this is the pass axis, say, then only these vibrations will be allowed to pass through and they will hit the second polarizer like this. So they are making an angle of 45 degrees. So this angle is 45 degrees. Now, as soon as the unpolarized light is incident on the first polarizer, the outcoming light will be I naught by 2. And when this I naught by 2 intensity light, polarized light, is incident on the second crystal polarizer with its axis making an angle of 45 degree to the vibrations of the polarized light, then the outcoming intensity I is equal to the initial intensity cos squared theta. Theta is the angle with which its axis is aligned to the incident plane of vibration. So I is equal to I incident cos squared theta. So you can apply this formula here, not here. This is unpolarized. So unpolarized light after passing through a polarizer, whatever be its position, because this contains vibrations in all directions. So after passing through the first polarizer, intensity will be I naught by 2. So substituting for this, I is equal to I initial is I naught by 2 cos squared 45 degrees. cos 45 is 1 by root 2, cos squared 45 is half, so I naught by 2 into half. So intensity of outcoming light is I naught by 4, and it is 25%. So 25% of light will come out of the second Polaroid.